Okay, so I'm there with the next thing is thermal stability. Now, if you pick up silicon or silicon germanium and you plot versus temperature, okay, beta of the device. So I'm going to put with temperature, beta of the device. Come on. Okay, so if I take beta with temperature, so let's put temperature on one axis. Okay, now I'm talking specifically about BJTs. Well, this is true about any PN junction. Okay, but I am talking specific to BJTs. But with any PN junction, the leakage is the issue. Okay, so for example, if you take a MOSFET, so drain to bulk, that leakage becomes important. That's why you have LDMOS, right? Okay, so leakage becomes important. Now, any PN junction, basically, you are working with thermal coefficients. Okay, so let's say beta, for example, beta of a device in silicon. Okay, so typically what will happen is there is a positive temperature coefficient for beta. Okay, so let's say beta goes up like that. Okay, for silicon, this is what's happening. For silicon germanium, this is what is happening. So this side is beta. Okay, so this is what is happening with beta in silicon or silicon germanium. Silicon or silicon germanium. Okay, now what is happening with case of a gas or a GaN, right? A gas or GaN is going to do this. So it is going to have a kind of a negative temperature coefficient. So gas or GaN is doing something like this. Or rather, let's put a red color. So this is a gas or a GaN thing which is happening. So this is just a trend. So I'm not putting any numbers there. And GaN. Now, what I'm assuming, why I'm explaining this is, I would expect that a lot of people will do silicon germanium designs. Okay, that's why I'm explaining this. They might use HBT. Okay, so how does it reflect when you look at the transfer characteristics, right? So what you expect for silicon and silicon germanium is going to be a transfer characteristics like this. You would go this way, and then there would be this way, and then there would be a thermal runaway like this, right? There will be a thermal runaway like this. Okay, so this is what's happening. Okay, so if you go and push more current, if you push more current, basically instead of doing this, okay, instead of doing something like this, they would go and do a kind of a runaway with a thermal. Okay, so it will be like this. Now, if I was to plot on this, what would a gas or GaN do? Because of self-heating, they would do this. They would go up, they would keep going up, and then they would start going down. So you would see edit points. You would see them do this on transfer characteristics. Okay, this is because one has a positive temperature coefficient while the other one has a negative temperature coefficient. Let me just. Okay, so one has a positive temperature coefficient, so these curves are going to look like that. So let's put another curve here for a different base current. Okay, so this is what a gas or a GaN would look like, while this is what silicon or silicon germanium would look like. So those who basically measure this device in the lab, they would see this. Okay, now what's the difference? This difference means that when you have a self-heating, then gas and GaN basically are, because of self-heating, they are having negative beta. That means that they are shutting down, or they prepare to shut down. Okay, so if you pick a big device and you try to power it up, and you boost the current, keep boosting current, the compression is going to be hard. The compression is going to be hard in case of gallium arsenide. So in case of gallium arsenide, let's put gallium arsenide. Okay, if I was to do P out, P in, so now this is transfer characteristics. I am doing collector current versus collector to emitter voltage, right? So this is what the waveforms would look like, right? For silicon germanium, the blue colored, and for gas and GaN, they will look like red colored. That means that when you hit it with power, the currents are going to go up, but because of self-heating, the beta would go down and the transistor would start looking smaller and smaller. That means if I take a gas device and do a gain, so I'm going to put a gain. Okay, so the gain is going to do, let's say it is biased more like a class A. So the gain is going to do a sharp compression like this. Okay, so this is what will happen in gas. In GaN, this starts far way back. So basically in GaN, I'll put a green colored curve. So in GaN, it starts far way back, like this. Okay, let's put it a green color. Okay, so now this compression is a soft compression. This is what happens with GaN. Insert, let's put this as a GaN. Okay, so when you choose GaN for your power amplifiers, you will face this soft compression. Okay. Okay, with gas, it is a much harder compression. Okay, so with gas, this is going to happen. With CMOS or silicon, with silicon or silicon germanium, okay, you are somewhere in between. Okay, the compressions are not going to be very harsh compression like this, or compression will not be like GaN. This will be somewhere in between. Now, what does it say about linearity? It means that I am expected to have much better linearity with the gas part. And SIGE people will not like this. Okay, so this is the red color, which is going to be silicon, or this is going to be silicon or SIGE. Okay, so that's what is happening. Okay, and this also basically you have to do a lot of corrections in here, and I will explain you how you do that correction. Okay, so this brings us to another topic of what is called ballasting. Okay, so ballasting is the topic. Okay, so now what is happening? Let's see this. If I was to use a gas or a GaN, it as soon as you start hitting compression or you hit it with power, because of self-heating, the compression is going to become bad. Okay, that's what is happening with gas and GaN. With silicon and silicon germanium, this is not what is happening. Okay, there's something else which is happening. So for example, if I take a big device, right? So a big device like this. So let's say physically the device is laid out in this area. Then let's split it up into two different areas, the core. Okay, so I'm going to make this core as a red one, or rather orange one or red one, doesn't matter. Okay, so a device is this big, but then when I start heating, when I start hitting with more power, then the core of the device starts heating more, and the beta is high. So beta is high means that the core will conduct more current, while the periphery is going to conduct less current. So what will happen is, because of the positive beta, the core will turn on more and more, while the periphery will turn off more and more. So what does it do? It causes what is called emitter collapse. Okay, so what is happening is, beta of the center guys are more than the beta of the peripheral guys. So the device would turn on more at the center and will switch off at the periphery. So when you hit it with power, it starts looking like a small device. So this guy basically then doesn't exist. You're looking at this device now. So thermal instability is a big issue with silicon germanium because of the positive beta. Then what do? You do ballasting, which means that you put resistor either in the base or in the emitter and bypass it with a capacitor. Okay, so when you put this resistor, you are balancing beta out between core and periphery. Okay, now if you put this in the source and bypass it with a capacitor, right, that is called emitter ballasting. If you do it with the base, that is called base ballasting. But then there is an issue with emitter and base ballasting across frequency. So if you are trying to make a broadband systems, you would prefer a emitter ballasting. If you're trying to do a narrowband system, you will be doing a base ballasting. If you are struggling with low frequency stability, you will be doing the base ballasting. If you are suffering with the high frequency instability, you are going to do emitter ballasting. So ballasting becomes important when it comes to silicon or silicon germanium for this reason. Okay, as the devices become big, their characteristics are not going to look like that, but I will draw you a characteristics, okay, for a emitter collapse. Okay, so a silicon germanium transistor, for example, it will build up like this, then at some point it will just break off. It will just break off like this, and then when it comes to breakdown, it will come up like that. Let me adjust this slope. Okay, let me adjust this one. So this is emitter collapse in silicon germanium. Okay, so this emitter collapse can be overcome with ballasting. With a large transistor, if you try to take the curves for silicon germanium device with large periphery, emitter periphery, this is what you're gonna get, not something like this one. So you understand that you do this for breakdown voltage, but then you do ballasting for the thermal stability. So this is what happens with silicon germanium, not with the gas or GaN. Okay, but then you can compare the compression characteristics of gas, GaN, and CMOS or bias CMOS or SiGe. So that's what's happening. So what I'm trying to make. Okay, the second topic for 1 hour was I was discussing various devices. I was discussing various processes. Now there is a lot more to processes. So for example, silicon or silicon germanium is going to be radiation hard. Okay, second, if you are in the bulk, okay, so then the noises are going to be low. So if you are going to do a PHAM device, for example, the noises are going to be low because the channel is in the bulk. MOSFETs are going to be very noisy because there is a silicon dioxide interface. Okay, while in PHAMs the channel is in the bulk. Okay, so the PHAMs are going to be less noisy than MOSFETs. Okay, so that's the difference. SBT will be less noisier than PHAM, not exactly. It will be somewhere in between because there are PN junction or the short noises dominate instead of a flicker noise dominating. Okay, so it depends on what noise dominates. Okay, so silicon germanium is radiation hard. Silicon germanium can be used for low noise applications. Silicon germanium can be used for making VCOs with very low phase noises, right? While gas and GaN are used because of the power density, they are used for amplifiers, right? And gas and GaN has this compression issue. Okay, silicon has a different compression issue, right? So all these things are there in case of different processes. Again, there are other things like wafer sizes. So gas and GaN is like 6-inch. That means that it is going to be more costly versus a 12-inch wafer or silicon germanium, right? So other limitations are there. Again, this is a self-aligned process. Okay, silicon germanium. This is a non-self-aligned process, so there is an alignment key, and then that means that all the fingers have to be either X or Y. While in silicon or silicon germanium, they can be either X or Y, or anything in mix them. While in silicon germanium, your hole and electron mobility depends on how you cut along what axis you cut the crystal. So basically, your holes may be accelerated in one direction, your electrons will be accelerated in a perpendicular direction. So you align all the PMOSs along X and all the NMOSs along Y to have the advantage of mobility. So these things are in the layout which you have to be, considerate. Okay, and if you are doing, for example, this one, okay, this guy, then these two should be in the same direction. The fingers should be in same direction. Otherwise, they will have different beta coefficients of temperature. So you are using this for temperature compensation, for example, somewhere. Okay, so this is related to temperature. Okay, so then these fingers and these fingers should be in the same direction. Okay, so a lot of things are there with silicon germanium about how do you align your fingers. Okay, so this is the basic difference between various processes. You can type your questions here. We will take a 1.5 hour break. We will meet at 2:30, and where we will start with the agenda. So I have covered two important topics here. One was on the software tools you are going to use. The other one was the process you are going to use. The next thing would be the system level. I would start explaining, right? So we will meet at 1:30. We'll meet at 1:30, and what I'll do is I would